questions on these that you'd like me to work out? Times 2, yeah. And then these 2's cancel. So you're left with the x equals negative 10. Any others? Not too bad? So you don't have to write this one down, but just so you know where the word geometry comes from. In Greek, geo means earth, and metria is to measure. So basically, geometry is measuring our physical environment. That's where that math came from. It is the first formalized mathematics, and it deals with physicality, physical objects, and then also space and relationships between them. Okay. We have, in geometry, we have definitions, we have theories, we have postulates, and then we have these things that have to be accepted as true without being defined. They're described. So we talk about points, lines, and planes. And the reason that we can't define them is because we can't actually see them. I can put a dot right there, and I can say that that represents a point. But a point is infinitesimally small. You can't see it. So in actuality, that dot that I put up there that I'm using to represent a point contains an infinite number of actual points. Just if that makes sense. They're just, think about, how many atoms are in the ocean. That's kind of the same idea. That's the ocean, and the real points are the little atoms inside of it. And a line, I can draw a line. But again, a line is made up of points, so it's not that thick. You can't see it. It's too skinny. So these are the definitions that you'll need to know. A point is a location represented by a dot. It's a location in space, but it's a microscopically, infinitesimally small location in space. It's a concept, not a reality necessarily. Okay, and we draw a dot, we put a letter on it, and we call it point A. A line is an infinite set of points represented by a string of dots continuing without end in both directions. So if you take points and you string them together, kind of like you'd make a beaded necklace, but it goes on forever. And the points are the beads. And we can name lines in 3 different ways. We can give it, if the line contains, any 2 points that you can pick, A and B, you can call it another letter M and call it line M. Or you can call it line AB, or you can call it line BA, because it's infinite and it goes in both directions, so it doesn't matter what order the letters go in on a line. Okay, so with the line, order doesn't matter. Not matter. Okay. Now, on other things that we're going to talk about, order will matter. So you'll need to keep track of which does matter and which doesn't. But in a line, the order doesn't matter. And then you have a plane. A plane is an infinite set of points, that should be plural, represented by a parallelogram, and it implies flatness. So a plane is basically, if you take a piece of paper, bless you, but it's an infinite piece of paper. Like this piece of paper goes on forever and ever and ever, both long and wide, just forever. That's a plane. So if you think of a piece of paper that's forever, that would be a plane. And it's drawn with a parallelogram. And it's 2 letters for a line, to name a line, 1 letter to name a point. So these are points. And for a plane, you have to have 3 letters or points. Or you have to assign it a name. So with this line, we assigned it the name M, or here we've assigned the plane the name M. Now the reason I know this is not a point and it's the name of the plane, points always have to have dots with them. Okay, so these are points. This is a name. So I can call this plane M or plane ABC. And there's not like a symbol, how we have a symbol for lines. There's not a symbol for a plane. You have to just say plane ABC, unfortunately. Any questions on that so far? Aside from being the final frontier, space is the set of all points. And it is 3-dimensional. So far, let me back up just real quick. We had a point. A point is 0-dimensional. Okay, a line is 1-dimensional. A plane is 2-dimensional because, right, it's a piece of paper, flat, 2-dimensional. And then space is 3-dimensional. So when you're talking about space, you're talking about 3D, you know, everything to the right, to the left, in front of you, behind you, and above you and below you. Space. Okay. So space is 3D. It's the set of all points. Okay. We have theorems in geometry. And like I said, geometry is based on terms that can be described but not defined, like points, lines, and planes. It's based on definitions. We have a lot of definitions. And then we have theorems and postulates. And theorems are statements that must be proven. Okay. Now, the theorems that you guys will be working with have all already been proven. There are theorems out there that have never been proven, like you guys might have heard of like Riemann's hypothesis ever? No? Okay. Well, there are these theorems that have never been proven, and if you were the mathematician that proved it, you're talking like millions of dollars in prize money and stuff because they've never been proven. They're that hard. But the ones you guys will be working with are all proven. Okay, a postulate is a statement that is accepted as true without proof. So let's take this soda. I could tell you it's cold. Would you need me to prove to you that this soda was cold? Or would you just take my word for it? Okay, well, most people would just take my word for it. The sky is blue. Planes are flat. You know, just things like that. Basically, these are things that when you think about them for a second, you go, well, yeah, that makes sense. Like you don't, it's intuitive. The theorems are the things that need to be proven. So we're talking about the sky being blue. I'd say the sky is blue, and I would say that the sky was blue because of refraction of light through water molecules in the air. Now you might believe me that the sky is blue, and that would be a postulate, and you'd just be like, yeah, the sky is blue, obviously. But then when I told you that it's blue due to the refraction of light through water molecules in the air, you might be like, okay, well, maybe prove it. And that would be the difference between a postulate and a theorem. Does that make sense? Okay. Then we have betweenness, and that is in or through the space that separates two things. So the air is between us, and there's a bazillion infinite points between us. So between is, you know, in between two things. And then you have intersecting, which is to cross each other, or the points that all figures have in common. So if you think about a road And an intersection in a road, that's where the lights occur, where the two roads cross each other. It's the same idea. We have two kinds of, you can have, a line can intersect a point. But 2 points can't intersect each other because they'd just be the same point. But a line can intersect a point. A line can intersect a line. A line can intersect a plane. And a plane can intersect a plane. And then you can have three-dimensional objects that intersect each other as well. Right now we're not going to worry about that. But when you have an intersection, where's my phone? The intersection is the same size or smaller than the smallest figure. Okay, so if a line and a point intersect, they intersect at a point. If two lines intersect, they can intersect at a point, like in this figure, or they can intersect and like lay on top of each other and intersect as at a line. The planes, these two planes can intersect at a line, or a line and a plane can intersect at a line. If I have a plane and the line lays on top of it, it's intersecting at a line. Or if the line cuts through it, it's intersecting at a point. So the intersection, the size of the intersection will be either the same size as the smallest figure or one size down from the smallest figure. So a line and a plane can't intersect and form a plane. They can't go bigger. They can only stay the same size or go smaller. Does that make sense? Okay. This is a ray. An array is basically kind of like half a line. It's infinite, but it only goes in one direction. So it starts at an end point. Okay, so here's our end point. And then it goes forever in one direction. Now with a ray, the order does matter. Okay, this first letter has to be the end point. Okay, now if I had this same 2 points, but my ray went this way, then that would be ray BA. Okay, so on a line, it doesn't matter because lines go in both directions, so you can flip the order, it doesn't matter. But with the ray, that first letter has to be the end point. It's really important because this, if you wrote this, but you meant this picture, you would actually be talking about this picture. It's a completely different figure. Does that make sense? So just be really careful with those on the rays. A segment is any part of a figure marked off as separate. It's a finite section of a line. So if you draw a line on a piece of paper, just like there's my line. I drew a line. I didn't actually draw a line because lines are infinite. I drew a line segment. And with this, the order doesn't matter. Because it's a piece. So this can be AB or BA. Now you'll see that with a line, you have a double arrow. With the ray, you have a single arrow, and with a segment, you have no arrow. And that's going to be important because, well, reality. People are lazy. We don't like to write a lot. Nobody wants to write the word line AB. They'd rather just write AB and put a line over top of it. It's faster, it's easier, it takes up less space, and it doesn't require you to use as much of your fingers. And same thing with ray and segment. And so they made these symbols so that you don't have to write the words line, ray, and segment every single time. But the symbols are very important. They matter. So you have to make sure that you know the symbols and that you're using the correct one. Okay, because line AB is not the same thing as ray AB. Okay. Segments are measurable. So far, lines, rays, points, planes, none of that has been measurable. The segment is the first thing that we're getting to that can be measured. Everything else is either infinite or too small. Okay. The endpoint is where the segment or ray stops. I already gave you that. So if you just want to label it, you don't have to write it down. That's okay. Those are endpoints. You have endpoints on segments and you have endpoints on rays. And length is the measure of how long a thing is. You don't have to write down the definition for length either if you don't want to. Just know that we're talking about measurable things when we talk about segments, and we measure them in length. So we have collinear points. Co is the prefix meaning together. Cooperate is to operate together. Cohabitate is to live together. Collinear is to be on a line together. So any points on the same line are collinear. You can have two or more collinear points. One point can't be collinear because he's not together with anybody. Okay. So A, B, and C are collinear. Non-collinear is points that are not together on the same line. A, B, and C are not collinear. Now, I could draw a different line. I could draw a line through A and B and make A and B collinear on a separate line, or I could make B and C collinear, or A and C collinear. But A, B, and C, all three of them, cannot be on the same line. There's no line I can draw that will go through all 3 points. I can draw a curve, but curves are not lines. Lines are straight. And then we have coplanar, and that is points on the same plane. We have coplanar points. So A, B, and C are all on the same plane there. And we have non-coplanar points. A and B are on the same plane, but C is not, so C is not coplanar to A and B. And you have coplanar lines. These two lines are on the same plane. And you have non-coplanar lines, where you have this line over here in the corner and this line that's on the plane. They're not coplanar. Remember, postulates are accepted as true. We don't have to prove these. This is just, yes, these are true. Okay. A line and a plane contain an infinite number of points. Okay. You guys have seen that art, pointillism? The Seurat, and he's got like the people on the park, and it's all made out of dots. All the pictures, just dots and dots and dots and dots and dots and dots. Well, obviously, if I keep making dots, eventually I could cover all of a piece of paper and beyond, and I could continue to make infinite dots, right? Or if I make a line of dots, if I could do this in a straight line, I would, but I can't, so, you know. This is one of those things where you go, well, yeah, that makes sense. It's infinite number of dots on the line, or an infinite number of dots on the plane. Okay. For any 2 points, there's exactly one line that contains them. So if I draw a point here, and I draw a point here, there's only one line that's straight, pretend, that can go through those 2 points. Just one. If I draw any other line, it won't hit both points. Okay. For any 3 non-collinear points, so if I draw 3 points that are not on the same line, there's only going to be one plane that can be drawn that will fit those 3 points. That's like if I put 3 dots on this piece of paper, or if I have 2 dots on this piece of paper and then I have 1 dot out in space, I'd have to like take a different sheet of paper and turn it somehow to get all 3 points on it. There's only going to be one piece of paper that would work. If 2 points are on a plane, there they are. Well, if they're on the plane and they're on a line, then the line also has to be on the plane. It's just like if I draw 2 dots on a piece of paper and I draw a line connecting them, the line is also on the piece of paper. It's not floating out in space. And if 2 planes intersect, they intersect in exactly one line. So 2 planes intersect. You can see how it makes a line? Yeah? Okay. So that's like that picture that was on the other page. They intersect and they make a line. Now planes can intersect and make a point, but there have to be at least 3 of them for that to happen, because you have like one coming in like this, one coming in like this, and then some other one coming in at like a weird angle, and it makes the point. But if it's just 2 planes, it's always going to be a line. So I'm going to try to draw that. Hold on. That's not very good. And then this would make a line, because the planes are infinite, so the line would also be infinite. Okay. It's just interesting. Okay, so remember I told you that geometry was the oldest formalized mathematics, right? And that's because it began in about 3000 BC. So geometry is over 5,000 years old. We don't know exactly, but it's over 5,000 years old. And it started with, it's measurements. So people they started to build civilizations, and so they needed to measure things to make buildings and roads and aqueducts and all that kind of stuff. And then they also started trying to measure the stars and looking at astronomy and things. They made the calendar a circle because they thought the year had 360 days, because they were, they're pretty close though if you think about it. They didn't have the ability to measure the way we have the ability to measure, and they got within 4¼ days of what it actually, or 5¼ days of what it actually is. And because they made the calendar 360 days and it's a circle, that's where the 360 degrees in a circle got created. So that's where it comes from, and basically the size of a degree was created to fit to that 360 degrees. Okay. We have the Chinese, the Greeks, and the Egyptians are all sort of working on geometric concepts. But it was all very loose. Math has always been discovered. It's never been invented except for imaginary numbers. Those are the only thing that's been invented. Everything else has been discovered. So what happened is in 300 BC, this guy named Euclid, you heard the name Euclid before? There's roads named after him, and we study what's called Euclidean geometry. That's what this is Euclidean geometry. It's geometry that exists in our 3-dimensional space. And in any case, he put together the first math book. So if you are really angry at math books, that's who you can blame, Euclid. He put together the very first math book. He called it The Elements. It's still used today. Like, you can still buy it. It's still being published today. That's how long this has stood the test of time. And Euclidean geometry is plane and solid geometry. So it's geometry that exists in our 3-dimensional world. And we need to talk about, well, we don't need to talk about it, but there's the reason you have to differentiate that this is Euclidean geometry that we're studying is because there are other forms of geometry that don't exist in our 3-dimensional space. There's hyperbolic geometry and there's elliptical geometry. And these are known as non-Euclidean geometries. and they don't exist in our realm of existence. Like, we live in Euclidean space. Like, you know, our houses are, you know, nice little cubes and stuff. That's all Euclidean. This stuff is not. Okay. Last little bit. We have to be able to sketch our shapes, and we have to be able to identify them. So if I want to say point Y is on line PQ, which is in plane T, you need to be able to draw that. Okay. So start with the plane, call it T. Don't put a dot on it because it's the name of the plane, not the point. Draw a line PQ, and then put point Y on it. Okay. Guys, I still got you for 5 more minutes. Stop. Okay. Line LM. So you need to be able to say, okay, it looks like that. Or like that. Okay. Let's go over these really quickly, and then I'll give you the homework. Okay. What's a statement that we talked about being accepted without proof? Postulates. Okay. A plane W, you need to be able to do this. And it contains points Y and point Z. True or false? 2 lines intersect and make a plane. False, right? Because they can only be themselves or smaller. And sketch and label a picture, 2 lines that intersect at point H. Now, your picture may not look exactly like my picture. As long as you have 2 lines, they intersect, and you draw a point and call it H. The lines can be going from any directions. Same thing here. If you put Y over here and Z up there, as long as you've got the information, the pictures can look different. Okay. So for your homework, do the first worksheet in the packet.